Hey kiddos, today we are going to be discussing functions in the real world. So, why is this applicable in your real world life? All right, so what we're going to be doing is I'm going to give you certain scenarios and we're going to sketch a reasonable graph showing this relationship, okay? So, things for us to consider dependent versus independent. Now, remember, your dependent is your y value, independent is your x value. And anytime you see the word depends on, it's going to always usually be the dependent value depends on your independent value, okay? Um, Increasing versus decreasing. So remember, increasing means that it rises from left to right. Decreasing means that it falls from left to right. And is there an asymptote? Okay, asymptote is an imaginary line that the function approaches but never actually touches. So let's jump right on in. Example 1. The time it takes you to get home from the Sunnyvale High School football game and the speed you drive are related. So, in other words, the time it takes you to get home depends on how fast you drive. So, notice me doing that, it shows that my independent value is how fast you drive, and my dependent value is the time. Key note here, typically anytime you have time involved, it's usually almost always going to be your dependent value. So this is our y, this is our x, and we just said that time is our dependent, so that will go there, and how fast we go, so I guess we would describe that as speed. Okay, so our graph, how would it look? So we would probably, sometimes writing number values helps. So notice that's 0, 0. I'll just go in increments of 5, 10, 15, 20, right? And speed. Let's see, we got 10 miles per hour, 20 miles per hour, 30 miles per hour, 40 miles per hour, 50 miles per hour, 60 miles per hour. So if I'm driving at 10 miles per hour, I'm probably going to be taking a long time to get home. Okay. So let's say it'll probably take me 20 minutes to get home if I live right around the corner of the school. Um, and normally what's going to happen there is I'd gradually go down. So if I'm going 20 miles per hour, it may only take me 15 minutes then to get home. And I'm going to keep gradually uh, going down. So notice my time, as my time goes down, my speed here is going to be increasing, essentially. Okay? So, um, notice I would probably never end up touching the x-axis. So that's that asymptote concept to think about there. So our graph would look something like this. All right? So as time decreases, all right, our speed increases. All right? Next situation. Example 2. You take roast beef from the refrigerator, okay, and you put it in a hot oven. So the temperature of the beef depends on how long it has been in the oven. So what we have here is temperature of the beef is our dependent, and how long it's been in the oven, okay, is our independent. Okay, so we're going to let this be our temperature. And this is one of those special situations where time is not the dependent. All right, so that's our temperature. And let's just, I'm going to make an imaginary line because that's the oven temperature. All right, very important to remember that we're taking this out of the refrigerator. Okay, so notice the temperature of the fridge. Okay, um, is something that we do have to consider. So what's going to happen is, as our roast is in the oven, so when we put the roast in, uh, it's going to be equivalent basically to 0. Um, so what's going to happen is we're going to gradually, as time goes on, okay, the temperature of the meat is going to gradually increase, okay? Because if it's in a hot oven, that means it's going to be getting heated up, essentially. I'm sure most of you cook or have cooked before, and you would know that that's what happens when you put something in the oven. It starts to cook and it starts to get hotter, so the temperature is going to rise gradually over time until it reaches eventually a certain temperature, and then it'll stay at that temperature. So that's what this graph would look like. The price you pay for pizza depends on the diameter of your pizza. Okay, I'm sure many of you have ordered pizza before. So we have the dependent, our y value, as the price that we would pay, and our independent value is going to be the diameter. So let's say I give myself some number values here. So that's obviously $0, $5, $10, $15, and let's say $20. And you can do the same thing with the diameter. You can have a 5-inch diameter, however they measure pizzas nowadays. 10, it just makes it easier to go in increments of 5, because this doesn't have to be really like realistic numbers. It's just to help me out here. So, notice no pizza is going to be free. So clearly I'm not going to start at 0 then. So if I have a pizza at a diameter of 5, then I'm probably going to be paying $5 for it. Hopefully not 20. So probably going to begin my graph here. And hopefully we would notice that if I get to 6, if I were to go to 6-inch diameter, it probably would raise the price. So what I should see is a graph that would look like this. Now, obviously, I'm not sure if you guys realize this, but most pizza places have a max diameter. All right. So they do have a particular size that they will make their pizza the biggest size that they possibly have, and they won't be able to go past that point. So we will have to keep that in mind here. But this is pretty much what our graph will look like. So the bigger our pizza, the more we would have to pay for it. All right, and now we're looking at your age and your height. Now, obviously, there are some outliers in these situations. Okay, um, so typically here, your age is your independent value, and your height is your dependent value. So I have height, and this is our age, and 0. Why not stick with my 5s? 5, 10, 15, 20, 25, 30, dot, 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 dot. And let's say we get to 80, right? Imaginary. Height, yes, you got your, let's say 3 foot, 5 foot, 6 foot, 7 foot, okay? Type of situation. So notice I'm just making this up, okay? So normally what happens is we all at birth have some sort of height to us. Okay, it may not be much, but we do have some height, and typically we grow taller and taller as we get older. Okay, and eventually you reach a certain age and you just stay the same. And then you reach another certain age, and sadly, you actually, they say, shrink. I know, I'm dreading that day. I'm already short enough. So they say that you shrink when you get old. Okay? I'm not sure what it is, but this is pretty much what our graph should look like. We begin at a certain height at birth, and as we do age, we do get taller and taller. Eventually, we will hit a plateau, and our height will stay consistently the same for a long period of time until we get a certain point of age where we're old. And I'm talking about way old, okay? And then we begin to shrink, okay? And I don't mean we shrink all the way back to itty bitty, but you do shrink a tad. So that is what this graph would look like. So that is functions in the real world.